Okay, so today we're going to continue on with sine law, but we're going to learn something really weird that happens in a very specific case called the ambiguous case of sine law. Let's get going. So first things first, we're going to do a very quick recap of sine law. I want you to remember that this is just used to solve for missing sides or angle measures in non-right triangles. So in other words, when you don't have a right triangle, any other kind of triangle, you can use sine law. However, you need to have had a known opposite pair. In other words, a side and the angle across from it that are both known. You cannot use sine law unless you have that opposite pair. Yesterday, I referred to that as the key. If you have that key, you're good to go. You can use sine law. Once we go through that, I'll introduce the ambiguous case of sine law. This is probably the most technical kind of thing that we're going to deal with in this trigonometry unit. But once you just get over one little hurdle with it, it's just like, okay, when do you have this ambiguous case? When does this happen? There's really only about one little trick that you need to remember with it. So we'll see how that goes. I'll try to explain it nice and slow when we get there. Let's get going. So first things first, this is a sine law question, rest assured. Completely solve this triangle. That means find all of the missing sides and all of the missing angles. I want you to pause the video here and give this one a try, and I will go over this in a second. All right, I'm going to go over this now. There's a couple different ways you could approach this one. I'll just show you the way that I would personally do this. First things first, I know this is a triangle that we know two angles and one side. When we know two angles inside of a triangle, we low-key actually know that third angle as well. So I think that's the easiest thing to solve here. So I'm going to start by finding that angle y. So remember that all the angles inside of a triangle need to add up to 180 degrees. So this third missing angle, so y, is going to equal 180 degrees minus the other two angles, right? So minus 80 and then minus 60. That's going to give me y equals 40 degrees. So right off the bat, I have one of my answers there, 40 degrees, and I'll even write it on the picture here. So that just leaves two things that are yet to be known, the small x and the small y. So for those side lengths there, what I want you to notice is that we actually have a known opposite pair inside this triangle. We know 60 degrees up here, and we also know the side length of 7 directly across from it. That's an opposite pair, and since both of those numbers are known, we can use it as a key, right? So just remember sine law, it is on your formula sheet. If you are looking for a missing side length, you use the version of sine law that has the side lengths on the top. That's the one that would look like this. A over sine capital A equals B over sine capital B, which equals little c over sine capital C, right? What this means is a side length divided by sine of the angle across from it equals any other side length divided by the sine of its angle across from it, right? This is a relationship that exists with sine law. It's really, really useful in these kinds of triangles. Let's get this to work. So since we know our opposite pair, since we know our key, as I would say, let's start with that. And again, since we're looking for some side lengths, we'll put the side lengths on the top. So I'll do it down here. With my key, I know we have a side length of 7 divided by sine of the angle across from it. So that's sine of 60. And let's suppose we want to find side x. So we're going to say that this equals x over sine of the angle across from it. Well, the angle across from it is 80, so sine of 80. And then we just need to rearrange this equation and solve for x. It's actually kind of nice when you're looking for a side length, because if you were looking for an angle measure, you'd not only have to rearrange the formula, but then also take the inverse sine of the answer. You don't have to do that when you're finding the side length. So let's see this one. So 7 divided by sine 60 gives me a number. I'm not going to bother writing it down. I'll just do this all in one sweep, and then I'm going to multiply it by sine of 80. Once again, as always, make sure you're in degree mode, right? This time around, I didn't tell you what to round to. That's kind of annoying. Just to spice things up, I'm going to round to the nearest hundredth. If you just rounded to the nearest tenth, that's fine. But I'll round to the nearest hundredth because why not? So x equals 7.96. And it doesn't look like there's any units here, so that would just be our answer there. Now let's solve for y. Y is another missing side length, so let's use our key with a side length on the top again. So 7 over sine 60 equals little y over the sine of the angle across from it. That's at 40 degrees that we found. So sine of 40. Always remember, you got to use those opposite pairs when you're using sine law, right? Anyway, to solve for y, we just need to multiply by sine 40 on both sides. So 7 divided by sine 60 times sine 40. And again, I just do it all in one go, because otherwise it's kind of just a waste of time, in my opinion. Anyway, y equals to 2 decimal places here. We have 5.20 is what that one would be there. Awesome. And that solves this triangle. We found all the missing side lengths and that missing angle that was in there. Awesome. So remember, with sine law, always identify your opposite known pair. If you can't identify one, see if you can find an angle using the 180-degree rule. And if you still can't do it, then that means you can't use sine law on that kind of a triangle. There's another tool that we'll use going forward. We'll introduce that another day. But you would, in that situation, have to use that other tool instead. Anyway, moving on. So this next example is a little bit weird. I'm not going to get you to do it on your own. This is kind of just going to lay the groundwork for what we're going to do for the rest of today. This example is saying find the absolute height, which we'll call h, of this triangle. By absolute height, we mean like literally like how tall would this triangle be? So if this triangle was like the side profile view of a mountain, and you were asked how tall is the mountain, you would just care from the peak straight down to the ground. That would be your absolute height. Now here's a nice thing, of course, in this triangle, because we have a nice flat base here, from the peak right to that base, we can tell that there's going to be a 90-degree angle down there. Let's kind of step back and look at this. If you kind of look at the whole grand picture here now, by drawing a line straight down for h, this has made a right triangle. And remember, inside of a right triangle, you can use those trigonometry tools that you would have learned back in Math 10C, whether it's Pythagoras or whether it's SOHCAHTOA, as we're all getting so sick and tired of writing down, SOHCAHTOA, right? In this case, since we know an angle and we don't know this missing side down here, that leaves us no option other than to use SOHCAHTOA here. So relative to this 25 degrees, our h right here is actually our opposite side, and 20 feet would be our hypotenuse. Opposite and hypotenuse from SOHCAHTOA, opposite and hypotenuse would be sine. So we'll finish this off by saying sine of 25 degrees equals your opposite side, which is h, divided by your hypotenuse, which is 20. To solve for h, we just need to multiply by 20 on both sides. So 20 times sine 25. And once again, it doesn't say what to round to. So you know what? Just 2 decimal places is fine today. Honestly, it's just like a mood for me. It's just like whatever I feel like on any given day. Really, I should throw in this booklet what you got to round to, but it is what it is. Anyway, 8.45 is going to be the height of this triangle. And actually, we do know units here. That would be 8.45 feet. Now, you might be wondering, where are we going with this? What was the whole point of that exercise? We didn't use sine law there. We just used stuff we did back in Math 10C. My point is on this kind of a question, and believe me that this will become important soon. My point is when you have a triangle that looks kind of like this, you can find the height of the triangle just by making it into 2 different right triangles, right? So the height of the triangle can just be made by drawing a line straight down and making it into right triangles, and then using SOHCAHTOA or Pythagoras from there. Now, the reason that that's important is because now we have a measurement just to compare the height of this triangle with the other sides that we've got going on here. We know that this 13-foot long side is longer than the height of the triangle. You probably could have assumed that though, because if you imagine if this could like pivot on this, like if this was a hinge right here and this side could pivot and swing, if you swung it towards this way, you'd see it go a lot longer down this way, just even visually, right? And also not a surprise because that's a hypotenuse of its own right triangle. And believe me, that's going to get important here. So let me clarify why we care. This is going to lead us into something called the ambiguous case of sine law. In case you're not aware what the word ambiguous means kind of like uncertain or unknown, or kind of like up in the air. We don't really know what's going on with this. Let me explain. The ambiguous case of sine law will occur when you have 3 things, right? And all 3 things here have to be met, because otherwise you won't have it. The first thing, and this is going to sound really dumb, but it is important, the ambiguous case will occur if you were not given a picture of a triangle. If I give you a question where I don't give you a picture of a triangle, there is a really good chance that it's an ambiguous case of sine law, but not guaranteed. You have to have these other 2 points as well. The second point is it has to be an SSA triangle. That means you have to have been given 2 side lengths and 1 angle that was not in between those 2 sides. Really, really important. The third point there, this one is the most technical. We'll get back to this in a second. Hopefully I'll find a way that's a little easier to remember this. The value of the side A opposite of your given angle A, so again, you're given an angle from SSA, the side length that's across from that needs to be greater than the absolute height, H, like what we just found in the last question, of the triangle. From this little example that we've got drawn over here, H, again, is that absolute height. I want you to notice that H could just be found by going sine A, I know it's backwards here, B times sine A, but take sine A, so sine of A, which would usually equal opposite, which is H over B, multiplied by B on both sides, though you'd have H equals B times sine A, right? So in other words, I'll say it again, your A side across from the angle that was given needs to be greater than the absolute height of the triangle. If you have all three of these things, then you have an ambiguous case of sine law, which basically means you actually have two different triangles to solve. Looking at this picture again here, I want you to notice that there's two side A's. I'm sure you already noticed that already. There's one kind of going inwards and there's one going outwards. For the most part, people would assume that a triangle looks more like this outwards one. I'll do it in red here. People would generally assume that a triangle would look something like that. But if your side length A is bigger than your height, theoretically, it could pivot on this little point up here and actually swing back down this way. Now, the reason it could happen is, remember, we are given two side lengths, A and B, as well as the angle that is not in between them, but we were not told how long this bottom flat side is. That flat side could be really, really long, or it could be really short. So it could be this long here, or it could just be this long here. We don't know because it wasn't given to us and we weren't given a picture to tell what this thing looks like, right? So if you have these three conditions, if I didn't give you a picture of a triangle to tell you what was going on, if you have an SSA triangle, so where you have two side lengths and the angle that is not located in between them, and most importantly, the value of the side A across from angle A, which will always be told with like a capital letter and a lowercase letter, so you won't get to miss that one up. The value of side length A needs to be greater than the absolute height of the triangle, which can be found just by taking the other side, B, multiplied by sine of angle A. This is weird, but when we do an example with this, hopefully it'll clarify it, of course. This is something that every single year I've taught the course, everyone always hates, not because it's necessarily challenging beyond what we already do. I'm not saying it's easy by any means, of course, but people usually dislike it not because it's challenging, but because it's a lot of work. And again, the reason it's a lot of work is you have two triangles to solve in this case. You've got that big one, but then you've also got this small one. Now, the thing that connects these two is this unknown angle over here. We'd call it B, right? Because it's across from lowercase b. In a big triangle, so our case one, you could say, so we'll call this B1, the angle would be an acute angle. It'd be less than 90 degrees. But if our triangle actually looked like this smaller one with A prime here, we could call this angle B2. It's going to be an obtuse angle. In other words, it's going to be bigger than 90 degrees. The relationship here is, and I didn't touch on this point already on purpose, the relationship here is you must subtract your initial angle B1 that you would find through sine law in a large situation from 180 to find the second possible angle. Or in other words, B1 plus B2 will equal 180 degrees because they're technically on the same line. And technically, if you were to like fit this in over here, it would still add up to 180 degrees, a straight line. That whole ramble there probably wasn't all that useful. This is going to be a lot better with an example, so we're going to jump into a couple here, right? Oh, sorry. First of all, before we do that, you can also use this fact of ambiguous case triangles to tell how many triangles you'll solve. So if you have an angle A, and side B, so you know a side opposite of an angle that was given to you, here's the situation that you got. You will only have one solution if your height of your triangle is the smallest side, and if your value of A is your largest side. So if the value of that side length across from the angle you were given is longer than that other side length there, you automatically can just say you'll have one solution. The nice thing about this, excuse me, the nice thing about this is there really isn't any testing you got to do there, because this will always be the case. If you automatically see that your opposite side is bigger than your other side here, you know you've only got one solution. Just to visualize this, if this side length A was bigger than B, like if it was a super long line, that was miserable. Oh my goodness. It's like a super long line. you can have it swing out this way, but if you were to swing it back the other way, it would be longer than side B, so you never actually get there, right? It wouldn't make any sense, so there's only one solution. It's just a really big, wide triangle. The one we really care about is you'll have two solutions. If the height of your triangle is smaller than that side A, that allows side A to like swing around and hit two different points, right? It's smaller than side A, but side A is smaller than side B, right? Now, here's a dumb way of remembering this. It works for me every single time. If you have HAB in that order, then you have an ambiguous case triangle. See, terrible pun there, right? You have a triangle, you have it. I don't know, I'm just kidding. Anyway, so that always helped me though. So if it's HAB in that order, you have an ambiguous case triangle. And then the one nobody likes, you have zero solutions if side A is the smallest side. And just to visualize that, I'll go extreme. Imagine side A was only like this long. Well, if side A was only this long, it's not even going to reach back down to this other side down here, right? It's going to be too short. So you're not even going to have a triangle at all. If your side A isn't even as big as the height of your triangle, you don't have a triangle. It doesn't make any sense, right? I don't know how I used to remember this. There was some joke I used to say about like Ahab, like from Moby Dick. Ahab, I don't know, maybe Ahab. Ahab's kind of like a pirate name, maybe a pirate name, excuse me. Maybe he's got like a peg leg, so he's like missing something. So I don't know. Then it just doesn't work. I don't know. So Ahab doesn't work. I don't know how you're gonna remember that. Good luck. You figure that out on your own. Anyway, we're gonna do an example here. So here's an example. First of all, we'll do all of these examples together because believe me, you're gonna need that. Suppose you have a triangle with angle A is 40 degrees, side A is 40 feet, and side B is 50 feet. How many possible triangles exist? Let me draw like a little sketch about what might be going on here. Let's start with our angle. I always do a flat bottom side here just so it makes things easier. 40 degrees is a decent angle, not quite that steep. It's more like this, I would say, 40 degrees. Since this is angle A, side A is going to be the other side over here. Notice though side B, which is the side going up here, is going to be 50 feet. So it's going to be a longer side. I'll do it about like that long, 50 feet. And then side A is only 40 feet, so it's going to be a little smaller. I'll try to draw it kind of like that. There we go. And I know this bottom line went a little longer. That's okay, because we don't know how long that other side is, right? This is 40 feet. Should put feet over here too. We can even label this B and A. And this would be like a little c if you really wanted to, and capital C over here if you really cared. But anyway, how many possible triangles exist? To answer that question, first of all, we know that A is smaller than B. Right? So automatically we know there's not going to be just one solution here. There could be two solutions or there could be zero solutions. Maybe 40 feet doesn't even reach down here. To figure that out, we have no choice but to calculate the height of this triangle. So imagine that there's a right triangle in here with the opposite side from 40 being your height. We need to solve for what that height would be. Since we're looking for the opposite side to 40 and we have the hypotenuse is 50, opposite and hypotenuse uses sine. So let's find this. Sine of 40 equals your height divided by 50, multiply by 50 here, so 50 times sine 40. This gives me a height of 32.1 feet. So let's organize these here. We have H, and we have A, and we have B. Write them out in order. The smallest number here is H. The next smallest number is A, because it's 40 feet, which is more than H. And then the next smallest number is B. So how many triangles do you think? Notice HAB. How many triangles do you think we have? Well, we have two, right? Because we have two cases or two triangles, whatever you want to say, right? It's ambiguous. That means this side 40 can also swing back over here, right? You would have two different triangles. I'll just change color really quick if it'll let me. You have your big triangle that we drew in the first place, but you could also have a smaller triangle that looks like this. Now, we weren't asked to solve for that or anything, so we don't have to, but just so you know, that means this angle B1 down here and angle B2, which is the corner angle down here, B1 plus B2 would equal 180 degrees. So if you just focused on the big red triangle right now, you could solve it using sine law because you have an opposite pair. You could use sine law to solve the whole thing. But then if you wanted to jump to this other triangle, you just have to realize that B1 plus B2 equals 180, or in other words, B2 would equal 180 minus B1. I know it didn't ask for that there, but I'm really going to drill this in as we go because we are going to be asked to do that in just a moment. I want to make sure you understand that. All right, here's another example. Suppose you have a triangle with angle A is 40 degrees, side A is 20 feet, and side B is 50 feet. How many possible triangles exist? Once again, draw this. It's the same angle from before, so I'll draw a bottom length here. The same angle, 40 degrees. That's our angle A. We were told side A is 20. We won't draw that quite yet, though. We know side B is 50. Oh, hey, that's the same as the last one. Okay, this is pretty much the same thing. The only difference here is side A is only 20 feet, right? Now, I drew it as like a little stumpy arm here, right? And I did that on purpose because since I knew that 40 degrees and 50 feet were already there, imagine if you drew the height of this triangle. Straight down like that. The height of this triangle can just be found by using sine again. So sine of 40 equals h over 50. And that's the exact same formula we had from before. So we know I don't even have to touch my calculator. H equals 32.1 feet. Write these side lengths out in order now. What's the smallest side length here? Well, of these three numbers, the smallest side length was A. Then the next smallest one was H. And the next smallest one was B. AHB. Oh, it's Ahab. Like from Moby Dick. It's like a pirate. He's got a peg leg. He's not complete. I don't know. I don't remember how I did that before. There's 0 cases is what I'm trying to say here, right? There are no cases to this one because it was Ahab and not Hab. We want Hab. We don't want Ahab. Hab is 2 cases. Actually, we don't want Hab. Hab is 2 cases, and there's going to be a lot of work when we have that, or when we have that. My mistake. But anyway, hopefully you get the idea. Just find your height of your triangle. After you draw it, just finding the height just is a matter of like doing a dotted line down and then using SOHCAHTOA. It's pretty much always going to be sine that you use on that. But anyway, just find the height of your triangle and then write them out in order. Really, the only ones you really have to remember here is Ahab and Hab. Anything else is just going to be 1 case, basically, or like nonsense. But I'm not going to give you total nonsense. 0 cases will be about as much nonsense as you get. Anyway, here we are, moving on. Okay, so it says example 2 slides. This is because I probably will need 2 slides to get this done. So I apologize if I start writing and then I go forward from there. I think in your note package, I give you a good amount of room, but even still conserve your room as we go through this. Follow along as we go, of course, though. Hint, hint. Suppose you have a triangle ABC. Angle A is 40 degrees, side B is 20 feet, and side A is 15 feet. Solve this triangle. Let's start by drawing a picture, right? As always. When I draw a picture, I always make sure my flat side is the bottom, and that'll be my unknown. I don't know how long that side is. I'll just start by drawing a flat base because it's a good place to start. Angle A, which I like always doing in the left-hand corner, 40 degrees. So once again, a 40-degree angle, something like that, 40 degrees, and I'll even call it A. There we are. We know side B is 20 feet. Let's just make this a little bit longer just so we have some room here. 20 feet, and that's my side B. And then side A is 15 feet. So side A has to be across from angle A here. So it's this side that kind of comes down. So I'll just draw it kind of like this. And that's 15 feet, side A. There we are. Now, notice this question did not give us a picture. Okay, so step 1, we were not given a picture. Step 2, this is a side-side angle triangle, an SSA triangle, right? That angle is not in between those other 2 sides. So that's step 2. Step 3, we should find the height of this triangle because we want to figure out how many solutions we have. Because we weren't given a picture and because it was an SSA triangle, it's very possible that we have no solutions. It's very possible that we have 2 solutions. Let's find out which one it is, right? So let's start by finding the height of this triangle. Notice when you draw the height of a triangle, you make a right angle. That means we have SOHCAHTOA. We can use SOHCAHTOA in a right triangle. So the height is the opposite side. 20 feet is the hypotenuse. Opposite and hypotenuse from SOHCAHTOA is sine. So sine of 40 equals height over 20. We want to solve for that height, so we just need to multiply by 20 on both sides. So 20 times sine 40, that gives us 12.86 feet. Now, what do you notice? Write these out in order. What's the smallest side that we were given here? It looks like it was the height, so height is the smallest. The next smallest is side A at 15 feet, and the next smallest is side B at 20. Uh-oh, we have an ambiguous case. Oh dear, this is our first ambiguous case that we are actually going to have to solve, right? So let's back up here. Since this is ambiguous, This means we could have a triangle that looks like the one I doodled right here. So a wide triangle like this, or we could have a triangle that once again has, oh, that wasn't so good, hold on. Once again has, that's even worse. Hold on, I'm going to try this one more time. There we go. Once again, it has a 40-degree angle, 40-degree angle, and that this is 20 feet, but it could be that that 15 feet comes swinging back that way, right? So we could have a wide triangle, or we could have like a really skinny triangle here. We got to break this down into cases. Let me tell you right now, a wide triangle is always the easiest one to start with. So I'm going to call this case 1. I'll do some work over here. I might have to do case 2 on another slide. Okay, so let me just go just like this. Case 1, always title them just to make sure I know where you're headed with this. Case 1, if you really want, we could redraw this triangle so it's a little bit bigger. 40 degrees. There we are. That's not so great, but hopefully you get the idea. 15 feet, 20 feet, 40 degrees. Also very important, label these using letters. That's capital A, that's lowercase b, that's lowercase a. Since this is lowercase b, this is going to be b over here. I'll call it B1 because this is case 1. This other angle up here will be capital C. I'll call it C1. And this side length that's unknown, this bottom side length down here, I'll call it lowercase c1. Since we're solving this triangle, we have to solve all of the pieces here. So there's 3 missing pieces here that we're going to have to solve. First things first, because this is an ambiguous sine law question, let's start by coming up with our opposite pair that is known. So we know we have this opposite pair here, 40 degrees and 15 feet. Let's suppose we want to start by solving for B1. I think that's really the only thing we can start with, because with C1, both capital C1 and lowercase c1, we don't know either of those, so we can't exactly use sine law on that. So let's start by trying to find angle B1. Since we're looking for an angle, we need to make sure the angle is on the top of our sine law. So we're going to set our key as sine 40 over the length of its opposite side, which is 15, equals sine B1, sine of angle B1, divided by the side length across from it, which is 20. So to solve for B1, we got to multiply by 20 on both sides. This is where things are kind of weird. 20 times sine 40. And then take that answer and divide it by 15. And remember, when you're solving for an angle, you're going to end up having to undo a sign. So you're going to get a really disgusting number first things first here. Always round to at least 4 decimal places. So when I went sine 40 divided by 15 times 20, I got 0.8571 is what that would round to. And that equals sine of B1. Now we want to get angle B1 out of there. To get rid of sine, we have to take the inverse sine, sine -1, of both sides. That'll cross out our sign there, and this is going to leave us inverse sine of that answer. And we'll just round to the nearest tenth, but in this case, it just so happens to round up. It's going to be angle B1. I'll make it a little more clear. Angle B1 equals 59.0 degrees. Put a box around it, and believe me, boxes are really, really, really needed here because you're going to have a lot of things you're solving for. Okay, so we know this angle, B1, 59 degrees. I'll even throw it into the triangle to make it a little bit more clear. Think about what we can solve next. We're looking for side length C1 and angle C1. We already know 2 angle measurements. We can solve for a missing angle measurement just by using the 180-degree rule. So capital C1 is going to equal 180 minus the other 2 sides. So minus 40 and minus 59. That's going to be really quick to solve. So 180 minus 40 minus 59. This gives me C1 equals 81 degrees. Put a box around that as well, because we want to make sure we don't lose that answer. I'll even draw it in my triangle just for good measure. We got one last thing we got to solve for here. We're looking for side length C1. We have no choice here because we can't use Pythagoras. It's not a right triangle. We have no choice here but to use sine law once again. Use your key. Okay. Remember, our key was our known opposite pair from the first place. We're looking for a side length this time, though, so we're going to want to put a side length on the top. So it's going to be 15, side length on the top, over sine of 40. That's sine of the angle across from it. That's our key. Equals the side length we're looking for, little c1, over sine of the angle across from c1, which is 81 degrees, as we just found. To solve for little c1, we just need to multiply by sine 81 on both sides. So sine 81 times 15 divided by sine 40. This is going to give me to the nearest 10th. It's actually a nice whole number again this time. That actually worked really well. Little c1 equals 23.0 feet. And that right there is going to be our answer. Okay, so I'm just going to hold you here for a second. Hopefully you can get that all jotted down and all that. And if you don't, just pause the video to make that work. But just to let you know what we've done here. We've solved case one. We've solved the triangle in which we are assuming it's a big wide triangle like most people would generally assume. But because earlier in this question, we determined that we have an ambiguous case. In other words, our height is smaller than A, which is smaller than B. Since we have an ambiguous case, that means we could have a case 2 triangle, that looks kind of like that, where that 15-foot side swings around and you have a much wider angle B2, right? That angle B2 in the corner, B2 being, you know what, let's even draw this again. I'm going to erase where I said case 2 here. Let's try to make this more clear with a bigger example. If case 1 looks like a wide triangle like that, oops, then that means case 2, which I'll just do in blue, would look something like this, right? This angle down here is going to be our B2. B1 was the angle over there. We already found B1, it's 59 degrees. The relationship between your case 1 triangle and your case 2 triangle is your B values. Angle B1 plus angle B2 will always equal 180 degrees because technically these two angles form the same straight line, the same 180 degrees, right? That is the only thing you really need to remember other than have on how to create an ambiguous case triangle. Jumping from case 1 to case 2 is just a matter of solving for B2. Okay, keep in mind, B1 was 59 degrees. I'm going to jump forward to the next slide because it's nice and clean. Let's worry now about case 2. So I'll draw just the case 2 triangle this time. It's going to look something like this. 40 degrees is still there. That was what was told in the question. We can't change the things we were told. We know this side is 20 feet, and then we know this side is going to swing back around this way at 15 feet. Let's label these sides so we don't get lost. This is going to be angle A. It has to be. That's what we were given. This has to be side B. This has to be side A. You know what? Maybe I shouldn't write that there. I'll write it just below it. There we go. That's a little bit better. What we do have now are some missing angles and missing sides. This angle in the bottom right corner will be angle B2. It's B2 because this is case 2, right? This angle up in the top corner up here will be angle C2. And then that means this side length down here that's unknown is side length C2. Hopefully you can see C2 is going to be a lot smaller than C1 was. C1 was assuming that C just kept going and going and going, like that side length was really long. C2 is going to be a lot smaller. Remember what I said just a moment ago, though? What connects case 1 to case 2 is your B angle, right? We remember from the first case that B1 was 59 degrees. Remember that when you are dealing with an ambiguous case triangle, B1 plus B2 needs to equal 180 degrees. So if you rearrange this, you can see that B2 is going to equal 180 degrees minus B1. So let's solve for that. B2 is going to equal 180 degrees minus 59 degrees. And then that means that B2 is going to equal 180 minus 59 is 121 degrees. Put a box around that, just like we did before, because we want to keep those answers good and straight. It's going to be kind of hard to write that in this here, but I'll do my best. 121 degrees. That should be pretty good. Now take stock of what we got left in this really skinny ambiguous case triangle. We know 2 of the angles. That means we actually low-key know that third number as well, right? So C2 can be found by using the 180 degree rule for a whole triangle. So in other words, let's just say C2 equals 180 degrees minus the other 2 sides. So minus 40 and minus 121. This means C2 is going to equal 180 minus 40 minus 121. C2 is going to be just a very measly 19 degrees. Put a box around that because we found that one as well. And I'll even try to write it in here, 19 degrees. Last but not least, we need to find side length C2. When you're finding a side length in a non-right triangle, your hand is played for you. You have to use sine law. Once again, though, even though we know that this side length is coming back in, we still have our same opposite pair from before. We still know 40 degrees and 15 feet across from it. So let's use that opposite pair with sine law. Since we're looking for a side length, we'll put the side length in our key on the top. So 15 over sine of 40 degrees equals our missing side length, which is C2, over its angle across from it, which is sine of just 19 degrees. We're almost there, I promise you now. I know how long this question was, but we now need to solve for C2 just by multiplying by sine 19 on both sides. So if we multiply sine 19 to the other side, we'll have sine 19, make sure you close the bracket on that, times by 15, and then take the answer to that and divide it by sine 40. And to the nearest tenth, I've got C2 equals 7.6, and I guess the units on that are feet, 7.6 feet. And put a box around that, and we can safely say now we are all done this question, finally. So just to take stock of this, one last time, this is the only ambiguous case question we're going to do today, just in case you're wondering. Just to take stock of what we've done, we'll go back to the beginning. I'll just go back, go back one slide here. There we are. What we did was we were given a question in which we were not given a picture. Once we drew our own picture, we were able to easily see it was an SSA triangle where we had two sides. I'll even, drop my pen. We'll even just circle that right over here. We had two sides and an angle that was not in between them. So that was step 2. And then step 3 was we found the height of that triangle right here, the height of the triangle, and we were able to confirm that the height was the smallest of those 3 sides. Matter of fact, it was HAB in that order. Because of those 3 things, that we weren't given a picture, that we had an SSA triangle, and that it was HAB, a HAB, because of those 3 things, we knew we had an ambiguous case triangle. When you have an ambiguous case triangle, you have to draw the large one like we did here. Call that case 1, solve it like you normally would. There's no surprises with that one. It's just an exercise of using a lot of sine law. But once you finish that case 1, you need to realize that you also had a case 2, a thinner triangle. What jumps from case 1 to case 2 is your B value. The value you got for B in the first triangle, which we can call B1, will directly be used to find your second B value in your smaller, skinnier triangle in ambiguous case called B2. You just have to subtract B1 away from 180 degrees to find B2. And that's because if you look at it on this last slide here, technically B2, maybe I'll change colors one more time to green. Technically B2 and B1 form the same total 180 degree angle on the same line. They divide a straight line equally because this B1 would actually be over here as well. Anyway, if you don't see that, don't worry about it. Just make sure you understand that B1 and B2 need to add up to 180 degrees. And it is that fact that connects your case 1 to your case 2. Nobody really likes ambiguous case triangles. They're an absolute ton of work, and it's kind of a mystery that you're given one in the first place. If you see a question where I don't give you a picture, there is a reasonable chance, not 100%, but a reasonable chance that it's an ambiguous case triangle. So always keep that in the back of your mind. Okay, we desperately need practice on this. So for today, your practice is your homework booklet. You can now do questions 1 to 7, and you can do question 9. You can't do question 8 quite yet. We're going to save that for a little later. If you'd rather just have some textbook practice, because at least the answers are in the back of that one, you can check your work. Page 108, questions 1 to 8. Those would be excellent practice. I highly recommend doing them. Don't just rely on the homework booklet, of course. That's like the very base minimum amount of work you can do in this course. Now, just a little bit of a brief thing. We have an upcoming quiz. Don't worry, for those of you in 2021 right now, don't worry. When I return to class, once I can, we will spend a lot of time going over this, and I will personally check in with each of you to make sure that you're getting this. But just so you know, the upcoming quiz, whenever that will be on reference angles, principal angles, trig ratios in the Cartesian plane, and sine law. And there will be an ambiguous case question on that quiz as well, so be careful. The quiz will only be one block though, just 40 minutes. So it'll be second half of the class whenever we do it. Remember though, we will have a full class where I'll go over all of this. Just make sure we're all good on this. So no panicking on that. Anyway, enough rambling for me. This is already a very, very long video. Best of luck, guys. If you need me, reach out to me over email, Remind, or Google Classroom. Best of luck.